Hi everybody, welcome to another video in statistics, section 9.2, estimating a population mean. Of course, we don't know the population mean, that's why we estimating it. And the next best thing is the mean of the sample. So the idea is always we use the statistic of a sample to estimate the parameter of a population. So in this case, we're talking about the mean. So the point estimate once again is the value statistic that estimate the values of the parameters. So in this example, we said the sample mean will estimate the population mean. So population is mu, the sample's mean is x bar. Right. So pennies minted after 1982 are made from 97.5% of zinc and 2.5% of copper. The following data represent the weight that treat the data as a simple random sample, estimate the population mean pennies minted after 1982. So that's easy. Put all of this into a list and then find one variable statistic of this one, give us the mean. Right, simple as that. Stat, edit, we'll just enter all those numbers, 2.46, 2.47, 2.49, 2.48, 2.5, 2.44, 2.46, 2.45, 2.49. Okay, where are we? 46, 45. Okay. 7, 5, 6. This will be 2.45, 2.46, 2.47, 4. Right. Let me check quickly. Right. And when we're done, second mode back to the home screen. Right, stat, calculate one variable statistic, list one, calculate. That's it. So the sample mean is 2.464. Right, simple as that. Right, next, in order to find to do confidence interval like we did on the previous section, we have different type of distribution, and this distribution is called the Stearns T distribution, or the T distribution. So the T distribution is defined as x minus the population mean divided by the standard deviation from the sample divided by square root of n. Now if we call this quantity as sigma, then we just have the mean minus the population mean divided by standard deviation. So this looks like the z-score. So and exactly z distribution. But in this case, that the distribution of the t will have the n minus 1 degree freedom. Of course, all the mean of the sample s is the sample standard deviation. So this is the sample mean, and s is sample standard deviation, and n is the number, the sample size. Right. So the way we after that is define the property of the distribution will be almost the same as the z distribution, right? The only difference is it has the degree of freedom, and the shape is a little bit different. So we do have the t distribution center 0, and it's symmetric about 0, so that is exactly like the z. The area under the curve is 1, exactly as z distribution. The area under the curve on the right and on the left, 1/2 each, exactly z distribution. As t decreases or increases with time bound, the graph approaching but never 0. So that the tail end, of course, flat out, exactly like z distribution. Right. The only slight difference here is the area of the tail of t distribution a little greater than the area on the tails of the normal distribution, which is the z distribution. And then next one, by the law of large number, when n increases, t will get closer to the standard normal curve. So the t will become z when the number is big enough, and the rule of thumb is when it's big enough is 30. So if n is equal to 30, then the shape of z and t are almost the same. Right, here's some shape. So the t is a little bigger on the tail, but we won't be able to tell if we just draw that by hand. Alright, the notation t alpha is the t value such that the area under the standard normal curves to the right is alpha. Right, so we talk the way we say t alpha, it is on the right end, on the right tail. But remember, in the calculation, when we do the inverse, like inverse normal, it is the area on the left. Kind of confusing. Like that. Alright, next, I'll find the t value such that the area under the t distribution to the right of the t value 0.2, assume 10 degree of freedom. So we have the area on the t values of 0.2, and it's on the right. And degree freedom is 10. And so in that case, n is equal to 11. Degree freedom is 1 less than n. Did I mention that? Yeah. So n minus 1 degree freedom. I underlined it, but that will be n minus 1. Right. Now just find the area. So we go to the calculator. T distribution, go to the T CDF if we want the area, and the lowest negative. Alright, the lower in this case 0.2, and we go to a very big number. That will do it. The degree freedom is 10, and then paste. We have 0.4227. Again, I will be TCDF for this example from 0.2 to a very big number. That will be enough. And then we have to specify the degree of freedom. Let's do that again. Second distribution, TCDF. Right. Now if we use stat range, go to stat, the t calculate. If we want the t, so t degree of freedom is 10. We want when it's greater than, which is on the right side of 0.2, and of course we have that same, we have the same answer as before, right? So be careful. On the stat range we can enter on the left and on the right, but when we use the TI calculator, it's just like a normal distribution. We have to enter. It works the way on the left, because we will find the t values in a little bit later. Right, but if we just want the area, specify the where we want the area. Right, of course later on we have to find the inverse values for the t as well. Well, we'll talk about that in a minute. Right, the confidence interval for the population mean. Now this is like what we have in the previous section, where we have the proportion, we have the point estimate, just one point. But it would be better if we can indicate an interval with some margin of error, and then the confident, how the level confident, how confident we are about the data. Right. So to find a confident interval for the population mean, we have to have this assumption that it have to be a randomized experiment. The sample size have to be small compared to the population, and the data come from the population is normally distributed or the sample size large. So either it is normally distributed population or the sample size large. By large we mean 30. If it's more than 30, that would be good enough. And then when we estimate the confidence interval, so this will be the margin of error. Just like what we have before, instead of t, we have z, and instead of standard deviation, we have s over square root of n. So population standard deviation s over square root of n. Yeah. Right. Let's look at an example. Construct a 95% confidence interval for the population mean. Assume that the population has a normal distribution. So we have to assume that, so we can use the t distribution. A sample of 20 part-time workers, so that will be n. So this is for the sample. This is what we get for the sample. N is equal to 20 and has the mean of the sample 3120 and standard deviation of the sample 677. Alright, so that's what we have. Next we want 95% confidence interval. So this is like what we did earlier. Right, so we want 95% confident. So 95% in the middle. That means we have 2.5% on each tail. So we'll find the z, or in this case the t values, alpha over 2. Right, so that will be second variable inverse t. The area, like I said, just like inverse z, inverse normal, the area is always on the left. So we have to say it 0.975, 97.5% on the left of it. Degree of freedom, here's n is 20, degree of freedom is 1 less than that. So degree of freedom is 19. And so we say t, that is inverse t, 0.975, 19. And that gives us 2.093. Right, so that's what we have for the sample and what we have for the t. The next part is for the population. We do not know anything about the population, but we estimate it. The best number we can come up with is the mean of that is same as the sample mean, right? So the statistic of the sample estimate the parameter of the population. So the mean of the population is estimated as the sample mean. and then the standard deviation for the sample. Use that to estimate the standard deviation of the population. So will be S over square root of n. S 677 over square root of 20. We have 151.3818. Right, so, and now the confidence interval. This is always the point estimate plus or minus the margin of error. The margin of error in this case is the t alpha over 2 times standard deviation. Right, so those two. Right, so we have this, the last number, this is standard deviation. So we have that number times the t alpha over 2. So let me just write out the math here. The mean 3120, t alpha over 2, 2.093, and standard deviation 151.3813, 13818, right? So I'm just typing exactly 3120. Let's clear this. 3120, that is the mean, and then plus the t alpha over 2. Where was that? I delete that already. That's fine. 2.093, the t alpha over 2 times the standard deviation of 151.3818. Right, and we have the upper bound 3436.8. The lower values, I just go ahead, copy that, and change to the negative or subtract. From 2803.2. Right, that's what we have. And we say, can we use a calculator for that? And the answer, of course. What we do here is like what we have earlier. Go to test, stat, and then test option number 8, t interval, right? So stat, go to test, t interval. Right, I'm going to choose the statistic here because that's what we are given. If we do not know about the statistic, we use the data, and just like the next problem, we enter the data into it. So it's fine. Choose the statistic here. The mean is 3120. Standard deviation 677. And the n, there 20. Confidence interval of 95%. We just calculate. Yeah, of course. That's what we have. Right, so that's what we use a TI-84 calculator. So if we want to use StatCrunch, this is what we go to. Right, go to stat, the t-stat, one sample with data or with summary. We have the summary of the sample, so we use this. Right, the sample mean 3120 sample standard deviation 677. The sample size there 20, and then check this box for 95% confident interval. This 95, so we don't need to change anything. Compute, yeah, so this will be the confident interval. Right, so simple enough. So that is where we have the summary of the sample. If we don't have the summary of the sample, we have like the data like this. There are two ways to do that. One, we put all of this into a list and get the sample mean and sample standard deviation. But it's much better just enter everything in here in the data. So for here, it's much better if we just go to the t-test. Sorry, there's no dash between the t and the test. Let's go to t-test and then just put the data in here, right? So first I'm going to enter the data in. So stat, edit, I'm going to clear the list 1 here, highlighted, clear, and enter. Right, 3.6, 4.5, 6.3, 2.6, keep doing that, 2.6, 5.2, 6.75, 4.25, 8, and 3. .6, 4.5. Where's the 2.8? Right. I forgot the 2.8, so it's okay to just enter that at the end. The number of the order of this number doesn't really matter. Right, so enter that when we're done. Second, quick. Next, go to stat, test, and option where it says t interval, and this time we choose data, and data come from this one. So we just, that's good enough. Yeah, data come from this one, and we just go ahead and calculate. All right, so that gives us if we want to, the mean of the sample is 4.7. So if we want to, if we do the one variable statistic, we have that. Yeah, of course, then we will do the t interval, and we choose that, and we input the mean and standard deviation. So this is like what we did before, but here once again, if we have the data, I recommend just go ahead and choose the data, come from whatever the list you enter already, and when it calculates, give us the confident interval. Okay, this is still, let's do that again. Right, 95% confident interval. So it's still the same. I'll calculate 3.3882, 6.0118. Yeah, so that is confident interval. Right, now I will try the StatCrunch also. Let's close this. So I will enter the data in one of the column. 3.6, 4.5, 2.8, 6.3, 2.6, 5.2, 6.75, 4.25, 8, and 3. On the homework, you just click a button and it moves the numbers into a column. We don't have to do type individually. All right, now go to stat, stat, t-stat, one sample, and this time with data. And the data, select column, from the variable 1, and then this time we calculate interval, confidence interval with 0.95, and then just compute. Right, so that's exactly what we have with the lower and upper limit. So this is the answer for the confidence interval. Right, so pretty much just like that. Right, now this will be similar to what we have earlier. Let's say if we have a margin of error, how many that we need to survey. Right, so that is the question about the sample size. So the sample size is required to estimate the population mean with the level of confidence is specified with the margin of error. So it's that. So that is the sample size. Right, let's look at this example. How large a sample would be required to estimate the mean weight of a penny manufactured after 1982 within the 0.05. So this is the margin of error. %99 confident. Right, we use that, we find Z. We did that multiple times, right? %99 in the middle. That means the tail end will be 1% on both ends together. So one end will be 0.5%. And we can find the Z alpha over 2. Notice that here we don't know the sample size, so we cannot really use T, right? The T is where we have the degree of freedom, which we don't know N, so we cannot know that. So here I'm just going to second variable, inverse normal, and the area on the left, 0.995, so 99.5%, and then we calculate, and that gives us 2.56. Okay, I just say 2.576, 3 decimal places. All right, so we have the Z. The standard deviation is 0.02 for the sample. Right, so that, and that we have to assume because we don't know what will be the sample size is. So we don't know the sample, so we cannot calculate that. So this have to be assumed, and usually that's based on the prior study. Anyway, put all of that together. This way. Right, so the Z 2.576 times the standard deviation of 0.02 over error, margin of error, and then we squared. I really don't need to put on the parentheses and bracket. We just say 2.567, or if we don't want to, just say second answer, because that's the last number we have, right? Second negative sign. That times 0.02 divided by the margin of error. Oops. That much. And then we just squared it. And we have 106.2, and always round up to the next integers. So that's what we have. Right, another example. Determine the sample size required to estimate the mean score on a standardized test within 98 points of the true mean with 4%. Wait. 94% confidence. Okay, we cannot be just 4%. Assume S is equal to 14 based on the prior studies or earlier studies. Right, so within 98 points of the true mean, so margin of error is 98, and 94% confident interval. So we have 94% in the middle. So that means if 95 in the middle, that means 6% on the tails. In particular, 3% on each tail. So you have 3% here on the left tail here. So with that, we will find the z alpha over 2, which is inverse normal. Of 97% on the left. So on one paste, right? 1.88. And with that, we have the sample size will be given by z alpha over 2 times s divided by e squared. So 1.88 times 14 over 98 square. There's something off here. Because if we do that, it's not going to be bigger than 1. So let's make a tiny change within 9.8. Right. Because if we divide by 98, yeah, the answer is decimal. It's not going to work. I'm sorry, but the problem is some typo with it. Right, 7213. So that's what we have. So round that up to 8. So obviously there's something wrong with the numbers here. I think I copied from the wrong prompt, but with that, yes, I will be 8. Right. So here's some summary. We write the t alpha over 2 corresponding to area on the normal curve to the right of alpha. So that's exactly the way we write z alpha over 2. So confidence interval, because that's the same way as we define for the estimate of the population proportion, kind of the same thing. The point estimate is for the population, it will be the same as the sample, and the margin of error is this. Where the s over square root of n will be that standard deviation of the sample mean. Right, and then if we want the find the sample size. That's what we have. Right, now let's look at some examples. Let t naught be a specific values of t. Find t naught so that the statement is true. Alright, so we're going to draw a t distribution. Of course, if I'm not telling you that is t distribution, there's no way we can distinguish between the t and the z by drawn by hand. Right, so let's say we have t naught somewhere in here, and we want the t bigger than that. Right, so t bigger than that, actually t naught, and we set this probability is equal to 0.05, and degree freedom is equal to 20. So what we need to find is this t. Well, that's just now inverse t, right? Right, the area, if the area on the left is that much, the area on the right will be complement of it. I'm just going to type here. That's fine. Degree freedom 20. That will do. Right, that gives us 2.845. Of course, if we do that by hand. Right, so pretty much. Right, so be careful that when we do the inverse t or the inverse normal, it's always enter the area on the left. If we use StatCrunch, we don't have to. If we want the t values, go here, calculate the t distribution. Right, we want the area to be 0.005, and where it is greater than, do that again, degree freedom 20, and the area on the right, when we hit compute, it will calculate the values here. Yeah, 2.85, exactly like what we did. Right, yeah, so on the StatCrunch we can enter the area on the right. We use this. On the left we use the less than or equal to for the left. Right, now back to the note. Find a critical value, t value that corresponding to 99% confident and n equal to 10. So we have a 99% confident interval, so will be 99% in the middle. That means each tail will be half of what remaining. So 1% on 2 tails, on 1 tail will be 0.5%. And degree freedom, when n equal to 10, degree freedom is always 1 less than n. For this case, 1 less than n, so 10 minus 1 is 9. Right, I'll just calculate. Second variable, inverse t, and this we have 0.995, because 99% and 0.5%. This just inverse t of 0.995. Degree freedom is 9. So that's all we specify. And then calculate. It's 3.2498. Right, so simple enough. Next, construct 90% confidence interval with the for the population mean. Assume that the population is normal distribution in the recent study of 22A greater. So we write out what we have for the sample. There are 22 of them with the mean is 19.6, and standard deviation of 5.8. So that's what we have for the sample. And in that case, we construct 90% confident interval. I'm just going to use the calculator here. So stat, go to test, and this is the t interval, option number 8. We use statistic here because we have what we are given for the sample. The mean of 19.6. Standard deviation is 5.8. N is 22. And we want 90% confident interval. Let's calculate the confident interval. Will be 17.472 to 21.728. Pretty much just that. Right, I just want to use StatCrunch as well. For StatCrunch, we go to stat, tstat, one sample. This time we use with summary. In this summary, the mean is 19.6. And standard deviation 5.8. Sample size of 22, and we compute the confident interval of 90% confident interval, and just compute. And here is the confident interval. Of course, that will be the same as we have with the calculator. Right. Now get back to the note. Next, we have the grade point average for 10 randomly selected high school students are listed below. So those are the 10 data points. Find 98% confident interval for the true mean. Right, so the true mean or the population mean, if you will. Right, so in this case we are given the data instead. So if we are given the data, when we do the stat test, we're going to choose the data. However, let's enter the numbers first. Stat, edit. That is the list one. I don't want to mess with that. If you want to erase, that's fine. Just go to the next one. 2, 3.2, 1.8, 2.9, 0.9, 4, 3.3, 2.9, 3.6, and 0.8. Two, 3.2, 1.8, 2.9, 0.9, 4, 3.3, 2.9, 3.6. Right, that. And now we go to stat, test, t interval. I will choose data. This time we get the data from list 2, so second, number 2. But yeah. And 98% confident. Calculate. And for the t interval, we get 1.5499, let's say 1.55 to 3.53. That's very big interval relatively, because the data is not that much. We only have 10 and we want very confident. So in that case we have to leave a very big interval. So if we have the smaller confident, if we have more data, then that interval will be tighter. Or if we want the confidence will be less than that, again the interval will be tighter as well. I just want to use the StatCrunch for this problem as well. I'm just going to enter that variable here, 2, 3.2, 1.8, 2.9, 0.9, 4, 3.3, 2.9, 3.6, 0.8. Alright, compute t-stat, one sample with data. The data come from variable 3 and confidence interval of 98%, and we compute. When we do that, we have the confidence interval is exactly like what we have when we do using the calculator. Right, now back to the note. Next, construct for the population mean. Assume that the population and normal distribution. A sample of 15 randomly selected mass measure has a point average and standard deviation. So fine of that. So in this case we are given the summary for the sample. N is equal to 15 and the sample has a point average of 2.86. So the mean is 2.86. Standard deviation for that sample is 0.78. Right, and with that we want 90% confidence interval. Right, I'm just going to use a calculator here. Second, the stat test, option number 8. Now we use the statistic. We not given the data, we have the statistic. This statistic, right? Calculate the mean 2.86, standard deviation 0.78. There are 15 of them, and the interval of 90%. Now calculate. We have from 2.51 to 3.21. So that is the confidence interval. Right, that's simple enough, right? One more. Right. The principal of the Riverside High School would like to estimate the mean of length of time each day that it takes all the buses to arrive and unload the student. How large the sample size need to be if we want 90% confidence interval, and error will be 7 minutes. So margin of error is 7, and we have the standard deviation for the sample. Right. We still need to calculate the z alpha over 2 for 90%. So 90% in the middle. That means 5% on each tail. And in that case, if we want z alpha over 2, so that is the inverse normal. Second distribution, inverse normal, and we want 95% on the left side of it. And mean 0, standard deviation from that pre-standard, and then paste. We have 1.645. After that, the sample size will be estimated as z alpha over 2 times s divided by e. Right. Yeah, will be that. Of course, I forgot the square. Right, to put everything we know here, 1.645 for z alpha over 2, standard deviation of 14, the marginal error 7 square. So 1 point, just say second answer. I don't have to type the whole thing again. Time 14 times 14 divided by 7, or I should just say times 2 and then square that. We have 10.82 22. So always round up to the next integers. So that will be 11. Right. So here's a little summary. If we want the estimate the population proportion, that is the assumption, and we use the confidence interval for p. And if we want to estimate the mean, if it is more than 30, we have to use if it is more than 30, so that's fine, that is normally distributed, and we just go ahead and just use the t for that. Okay, that's really confusing. All right, so bottom line is we did not cover that part. So bottom line is the simplest form is if we estimate the population proportion, it will be under one proportion z interval, and if we want to do the confidence interval for t, that t interval, right? So that's just a summary of it. Right. With that, we finish section 9.2. As always, thank you for watching, and see you in another video in statistics.